Okay, hai semua. So, di dalam video ini, Madam akan terangkan mengenai satu lagi subtopik, which is if we look at the learning outcome, this is the last topic, which is common ion effect. Now, when it comes to common ion effect, we are going to study the effect of common ion. Common ion ni dalam bahasa Melayu is ion sepunya. Dalam arti kata lain, kita akan lihat apakah kesan bila kita masukkan insoluble salt di dalam larutan yang mempunyai ion yang sama. So if you still don't get what is meant by the title, okay, let's see. For this, alright, do you remember that usually I will ask you guys to calculate the KSP and the S, which is the solubility? Okay, that is actually a questions where we add the insoluble salt in water. For example, okay, Madam ambil argentum chloride. So usually we are going to add argentum chloride. Oh, but before that, argentum chloride is insoluble salt. Okay. And then you add in water. And usually the question that we'll ask is, what is the solubility? Okay, this is the question that you have learned how to calculate and to find the solubility in the past few days ago. Okay, so that one is in water. But how about if we add argentum chloride in sodium chloride? What will happen to the solubility? Okay, so what is the difference between water and salt? Now, water only contains H plus and OH minus. And we know that argentum chloride consists of Ag2 plus, we only have argentum ion and chloride ion. So if we compare argentum ion, chloride ion, hydrogen ion, and hydroxide ion, is there any similarity? Is there any ion that is common? The answer is no. Okay, there's no 4 ions that have the same ion here. But let's take a look at this example. Now, in sodium chloride, we all know that sodium can produce sodium ion and chloride ion. Now, let's see. We have argentum ion, we have chloride ion, we have sodium ion, and we have chloride ion. Do you see any common ion here? Yes, the common ion in this solution is chloride and chloride ion. So this is what we call as common ion, ion yang sama. Now, does it affect the solubility? In fact, yes, it will affect the solubility. So will the solubility increase or decrease? Okay, so let's relate with Le Chatelet. Now, we know that argentum chloride, if it dissociates in water, it will only dissociate partially to produce argentum ion and chloride ion. Okay. Now, according to Le Chatelet, if you still remember, if you can relate with chapter 6, since there is a common ion here, which is chloride ion, that means we are adding the concentration of chloride ion. So what will happen? Now, this is the disturbance. Okay, disturbance. So what happened? Chloride ion will increase. when chloride ion increase, okay, let's make something additional of chloride ion will disturb the system. Okay, this is what you learn in chapter 6. Okay, the system is not at equilibrium. To reattain the equilibrium, the reaction will shift to the left. Okay, let's take a look at this point. The reaction will shift to the left. Now, as we know, when this increase, okay, this increase means the chloride has a lot in the system. So it is not at equilibrium. So to reattain back the equilibrium, as this is so much over here, then it must be used. We have to use all the chloride. So to use the chloride, it must react with argentum. So what happened? This chloride react to argentum to produce AgCl, and that is what is meant by shifting to the left. And I bet you guys understand this since you learned Le Chatelier before. It shifts to the left. What will happen when it shifts to the left? Argentum chloride will be produced. Okay, argentum chloride will be produced. Now, since the reaction shifts to the left and argentum chloride will be produced, what happened? The solubility will decrease. Yes, definitely it will decrease because now it shifts to the left and it produces more solid. Okay. Okay. Quick revision. If it shifts to the right, means it's soluble more. If it shifts to the left, it produces more solid and therefore the solubility will decrease. So when it comes to common ion, we know that when it comes to common ion, whenever we add insoluble salt in a salt with a common ion, it will definitely decrease the solubility. So the answer will be the same. If the question asks you, it will give you the same answer, that the solubility will decrease. But for you guys, you have to prove it. Okay? You must prove it through calculation. So I'm going to teach you how to calculate the solubility in common ion. So, yeah. Okay, let's take a look at this question. Now you are given the Ksv for argentum chloride is 1 exponent negative 10. Calculate the molar solubility of argentum chloride in water and a solution of 0.1 mole potassium chloride. Okay, so let's do one by one first. Now let's start with the solubility of argentum chloride in water. So this is just the same thing like what you have always done before. The difference is previously it doesn't mention about water, but you know that it is in water. But in this case, this is we want to see the solubility in water. So always start with equation. And chloride ion. Okay, so we know initially, okay, this one, solid has no concentration. Initially, there is no dissociation, so the concentration will be 0. Changes. So we know this one will add plus S plus S. S is referring to the solubility, and at equilibrium, it will be the same. So this is the ice table. S. Now, express your KSP. KSP equivalents to argentum ion and chloride ion. Now, we have the KSP, which is 1 exponent negative 10 m squared. So this is your S. This is your S. So S will be 1 exponent negative 5 molar. So we can conclude that the solubility of argentum chloride in water is 1 exponent negative 5 molar. Okay, so this is it. Now let's take a look what will happen to the solubility of argentum chloride when we add in 0.1 molar of potassium chloride salt. So, as we know, potassium chloride is a soluble salt. Okay, it's a soluble salt. Therefore, it will dissociate 100%. Instead is in aqueous, it will produce potassium ion and chloride ion. So the common ion here is chloride ion. Now, the initial concentration is 0.1. So this is 0 and 0. This is final because it is 100% dissociate. So in the end, potassium chloride will become 0. So this will be 0.1 and 0.1. So as you can see, there is an additional of 0.1 molar of chloride ion. Now, let's go this. This is the ice table when it happens in water. However, in this time, okay, this is still correct, but when it comes to changes, there will be a slightly different here where it is still positive S, but addition with another 0.1. So our S here, maybe I can put the different here, positive S plus 0.1, and therefore at equilibrium, instead of only S, it has 0.1 because of the additional of the common ion here. Okay, now let's calculate using the KSP. In this case, this part will be S plus 0.1. However, because solubility is very small, since S is too small, okay, it is very small, the solubility is very small, therefore we can assume that S plus 0.1 is just 0.1, which means we can ignore the S. S is negligible because it's very small. So let's calculate back. Okay, if you calculate this, therefore you're going to get this. There's a different value. For common iron, the solubility will be 1 exponent negative 9. But if you look at the one in water, the solubility is 1 exponent negative 5 molar. We'll compare about it later on, but let's complete our answer. The solubility of argentum chloride is 1 exponent negative 9 molar. Now, let's start compare. So this is the two situation. The first one in water and the other one in potassium chloride. So like what I explained before, in water there's no common ion, as you can see, no common ion, and this is the solubility. For potassium chloride, the common ion is chloride ion. And when we calculate, the solubility is 1 exponent negative 9. So what we can conclude is, when we have the common ion, it will reduce the solubility. See, this one is 1 exponent negative 5. This is 1 exponent negative 9, which means this one soluble more. Okay, it dissolves more, it's soluble more. But with the existence of common ion, it reduces the solubility, and it is proved by this calculation. So there you have, this is our qualitative, which is the explanation, and you prove it through the calculation.